The entire universe was once smaller than a single atom. This story of cosmic origins is the greatest detective case in all of science. You are about to journey through 25 incredible discoveries that have completely reshaped our understanding of the Big Bang and its mysterious inflationary beginning. You will gain a complete picture of how our cosmos went from a tiny speck to the vast expanse we see today. We will uncover why the afterglow of creation looks the same in every direction, and what strange force stretched space itself faster than light. What is the one cosmic mystery you find most compelling? That faint static hiss from an old television set holds the echo of creation itself. It was the year 1964, and two radio astronomers named Arno Penzias and Robert Wilson were troubleshooting a persistent, maddening noise in their giant horn antenna in New Jersey. They pointed it at the sky and the noise was there. They pointed it at New York City and the noise remained. They even famously scrubbed away a layer of pigeon droppings from the antenna, convinced it was the source of the interference. But the hiss never went away. It came from everywhere, a faint microwave signal bathing the entire cosmos. They had accidentally stumbled upon the cosmic microwave background, the oldest light in the universe. This is the remnant heat from the Big Bang, cooled and stretched over nearly 14 billion years into a frigid glow just a few degrees above absolute zero. It is the afterglow of the fireball that birthed everything, a fossil imprint from a time when the universe was a hot, dense soup of particles and energy. This discovery was the smoking gun for the Big Bang theory, finally tipping the scales against rival ideas about a steady-state universe. Yet this incredible snapshot of the infant cosmos presented cosmologists with a profound and troubling mystery. Why is this background glow so incredibly uniform? No matter which direction you look in the sky, the temperature of this ancient light is the same, to within 1 part in 100,000. This near-perfect uniformity should have been impossible. For the universe to reach this even temperature, every region of space had to have been in contact, had to have exchanged heat in the distant past. But in the standard Big Bang model, there simply had not been enough time for light to travel from one distant region to another to even things out. It was as if you had 2 cups of coffee, one in London and one in Tokyo, that cooled to the exact same temperature without anyone ever moving them. How could the entire universe have coordinated itself so perfectly? The answer to this cosmic conundrum would lead to one of the most radical ideas ever proposed, a concept that rewrites the very first moments of time. This perfect sameness is the horizon problem, a paradox that cuts to the very heart of cosmic history. Think of the universe we see in the cosmic microwave background, a vast sphere of ancient light. On one side of this sphere, there is a patch of sky. On the exact opposite side, another patch. According to the standard Big Bang timeline, these 2 regions are so far apart that light, even traveling at the ultimate speed limit from the moment of the Big Bang, could never have bridged the gap between them. They existed beyond each other's cosmic horizons, forever isolated. They were like 2 islands in an ocean that had never been connected by any bridge or boat. And yet, these 2 separate islands decided to set their thermostats to the exact same temperature, with a precision that is almost impossible to believe. How could they have possibly coordinated this? Without some form of communication, you would expect one region to be slightly hotter or colder, a relic of random fluctuations from the violent birth of everything. The fact that they are not suggests that the universe, in its infancy, must have found a way to connect these seemingly disconnected realms. The standard model was missing a crucial chapter, a mechanism that allowed the entire cosmos to chat and agree on the rules before being ripped apart. This glaring flaw in an otherwise successful theory was the clearest signal that our story of the beginning was incomplete, setting the stage for a theoretical leap that would redefine the concept of a beginning itself. This perfect uniformity was not the only cosmic puzzle. scientists soon uncovered another mystery, one hidden in the very geometry of space itself. We call this the flatness problem. To understand it, you have to think about the ultimate fate of the cosmos. General relativity tells us that the fabric of space can be curved by the matter and energy within it. This curvature can take one of three possible shapes. Space could be positively curved like the surface of a sphere, eventually looping back on itself. It could be negatively curved like a saddle, bending away forever, or it could be perfectly flat like an infinite sheet of paper. The shape is determined by a tug of war between the energy of the universe's expansion and the pull of its own gravity. For space to be flat, these two forces had to be balanced with almost impossible precision from the very first moment. Think of it like balancing a pencil perfectly on its sharpened tip. If you place it with even a hair's breadth of deviation from absolute vertical, it will quickly topple over. The universe is that pencil. Any tiny deviation from perfect flatness in its earliest moments would have been wildly magnified over billions of years of expansion. If there had been slightly more matter and gravity, the cosmos would have collapsed back in on itself in a fiery big crunch long before stars could form. If there had been slightly more expansion energy, the universe would have flown apart so rapidly that galaxies never could have coalesced. Yet our most precise measurements show that the observable universe is flat too, within a margin of error of just 0.4%. It is balanced on a knife's edge. For the standard Big Bang model to explain this, the universe must have been fine-tuned at 1 second old to a precision of 1 part in 10 to the power of 60. That is a 1 followed by 60 zeros, a number so astronomically unlikely it defies all reason. It suggests our universe did not simply luck into this perfect balance. Something happened in that first second to actively force it onto this razor-thin path of flatness, setting the stage for the cosmos we inhabit today. The solution to these twin paradoxes arrived in a theory of breathtaking audacity. It suggested that the universe did not simply expand, but for a fleeting instant it exploded. This is the theory of cosmic inflation proposed by physicist Alan Guth and others. In the first tiny fraction of a second, a minuscule fragment of time so brief it is almost meaningless to write it down, the cosmos underwent a period of hyper-accelerated expansion. Space did not just grow, it stretched at a rate far exceeding the speed of light, doubling in size again and again in an exponential frenzy. This was not an expansion of matter into space, but a violent stretching of space itself. The entire observable universe, all the galaxies and stars we see today, were inflated from a speck of space far smaller than a single proton. This primordial patch was so tiny that it had ample time to reach a uniform temperature, to chat and equilibrate before inflation ripped it apart. Then, in that incredible burst, this tiny, smooth, and balanced region was stretched to cosmic proportions. The horizon problem vanished because every part of our sky was once intimately connected in that minuscule original dot. The flatness problem was solved because inflation acted like a cosmic iron, stretching the fabric of space so tremendously that any initial curvature was smoothed into what appears to us as perfect flatness, just as the surface of a balloon appears flatter and flatter as you blow it up. This single, elegant idea rewrote the opening chapter of the cosmos, but it raised an even more profound question. What could possibly possess the fabric of reality to behave in such an extreme way? But for inflation to be more than a clever story, it had to make bold predictions. A theory that cannot be tested is merely a philosophy, and inflation offered a set of very specific, very precise forecasts about what our telescope should see. Its first and most fundamental prediction was that the universe must be geometrically flat. Remember that cosmic pencil balanced perfectly on its tip. Inflation's incredible stretching would have smoothed out any initial curvature, forcing the universe onto that razor's edge of flatness, a condition that subsequent observations have confirmed with stunning accuracy. But the predictions went even deeper, reaching into the subtle textures of the cosmic microwave background itself. Inflation declared that this ancient afterglow could not be perfectly uniform. It must contain tiny, microscopic variations in temperature, imprinted like a cosmic fingerprint from the quantum frenzy of the inflationary epoch. In the seething energy field that drove inflation, quantum fluctuations were inevitable. Tiny, random ripples in energy were happening everywhere all the time. Under normal circumstances, such a ripple would be a fleeting, insignificant event. But inflation's hyper-stretching of space acted like a cosmic magnifying glass, taking these subatomic wrinkles and blowing them up to astronomical sizes. These amplified quantum ripples became the seeds for all future structure in the universe. The slightly denser regions would, over billions of years, pull in more matter through gravity, eventually growing into the vast cosmic web of galaxies and galaxy clusters we see today. Without these initial imperfections sown by inflation, the universe would have remained a featureless, sterile sea of gas. Our very existence hinges on those primordial imperfections. And there was a third, even more profound prediction. The violent stretching of space during inflation should have shaken the very fabric of spacetime, creating ripples known as primordial gravitational waves. These are not waves in water or air, but literal distortions in the geometry of the universe itself, echoes of the inflationary explosion. Finding these waves would be the ultimate confirmation of the theory, a direct line back to that first unimaginable moment. These three predictions transformed inflation from a speculative idea into a robust scientific framework. It was no longer just a solution to old problems. It was a theory that laid its cards on the table, telling observers exactly what to look for. The hunt was on. The hunt for these cosmic fingerprints required a new generation of eyes, instruments that could see the ancient light with a clarity far beyond our earthly limitations. Enter the Boomerang and WMAP missions, two pioneering spacecraft that would stare deep into the cosmic microwave background and read its story like a history book. Boomerang was a balloon-borne telescope that floated high above the Antarctic, above most of the obscuring water vapor in our atmosphere. It was designed to measure the subtle temperature differences in the CMB across a small patch of sky with incredible precision. What it found was a resounding confirmation of cosmic flatness. By studying the apparent size of the hot and cold spots in the ancient glow, scientists could determine the underlying geometry of the universe. Think of it like this: the patterns in the CMB are like a cosmic ruler. In a positively curved, closed universe, the ruler's markings would appear larger than they truly are. In a negatively curved, open universe, they would appear smaller. But Boomerang saw the spots at exactly the size predicted for a perfectly flat cosmos. The universe was not a sphere or a saddle, it was an infinite-seeming sheet. This was a monumental victory for the inflationary model, but it was the Wilkinson Microwave Anisotropy Probe, or WMAP, that truly revolutionized our view. This satellite mapped the entire sky, producing a full sky picture of the cosmic microwave background with breathtaking detail. Its data did not just confirm a flat universe, it revealed the specific patterns of fluctuations that were the hallmark of inflation. WMAP measured the tiny temperature variations, mere millionths of a degree, and showed they followed a very particular statistical distribution. They were almost but not perfectly scale invariant. This means the fluctuations were roughly the same strength across all distance scales, a direct prediction of the simplest inflationary models. It was as if inflation had left a unique signature in the static, a specific rhythm to the hiss that perfectly matched the theoretical forecast. The data from these missions provided a stunningly precise fit to the inflationary picture, turning a bold hypothesis into the cornerstone of modern cosmology. The universe was flat, and its initial seeds were sown by quantum fluctuations stretched to cosmic proportions. Yet, with this profound confirmation came a new set of mysteries. hidden within the very data that had seemingly solved everything. The WMAP map was a revelation, but the Planck satellite would soon deliver an image of the infant universe with a clarity that felt almost like looking at the face of creation itself. Launched by the European Space Agency, Planck was the ultimate cosmic cartographer, designed to measure the faint whispers of the cosmic microwave background with a sensitivity that dwarfed all previous efforts. Its mission was to read the fine print in the universe's birth certificate, and what it found would both confirm our deepest theories and introduce new, profound puzzles. Planck's map revealed the temperature variations in the ancient light with a precision of a few millionths of a degree. It was like upgrading from a grainy black and white photograph to an ultra-high-definition color image. Every subtle swirl and dimple in this cosmic backdrop carried information about the universe's composition, its age, and its ultimate fate. Planck's data refined the key numbers of cosmology to an astonishing degree. It told us the universe is 13.8 billion years old with a margin of error of just 1%. It confirmed with even greater certainty that ordinary matter, the stuff of stars, planets, and us, makes up less than 5% of the cosmos. The rest is the mysterious dark matter and the even more enigmatic dark energy. For the theory of inflation, Planck's findings were a double-edged sword. On one hand, they provided the strongest evidence yet for the core idea. The pattern of fluctuations Planck observed matched the predictions of simple inflationary models with spectacular accuracy. It was the final, definitive confirmation that quantum jitters, stretched to cosmic scales, were indeed the seeds of all structure. Yet, on the other hand, Planck placed the most stringent constraints ever on the specific mechanics of inflation. Many of the more exotic and complex versions of the theory, those dreamed up by physicists over decades, were now ruled out by the data. The universe, it seemed, preferred a simpler, more elegant kind of inflationary beginning. This refinement was a crucial step. It brought us closer than ever to understanding the exact mechanism that drove the cosmic explosion. By eliminating a vast swath of possibilities, Planck guided theorists toward the most plausible scenarios, focusing the search for a final, fundamental theory of the universe's first moment. Yet, in its incredible precision, the Planck data also revealed subtle anomalies, features in the cosmic background that the simplest models of inflation struggle to explain. The map was almost perfect, but its faint, unexpected imperfections whispered that the story of our cosmic dawn may still hold secrets we have only begun to glimpse. Among the faint temperature variations mapped by Planck, there was a subtler, more elusive signal hidden within the light's very orientation. This is the story of B-mode polarization, a ghostly imprint left on the cosmic microwave background by the most violent event in history. When light travels through space, its waves can vibrate in specific directions, a property known as polarization. The cosmic microwave background light became polarized when it first streamed through the hot, dense plasma of the infant universe interacting with electrons. Most of this polarization creates a curling, vortex-like pattern known as E-modes, but a different, far more significant pattern was predicted, one that could only be created by a titanic shaking of spacetime itself. These are the B-modes, a twisting signature in the light that acts as a direct fossil imprint of primordial gravitational waves. These are not waves of light or sound, but literal ripples in the fabric of the cosmos, generated during the explosive stretching of inflation. Detecting them would be like finding the crater from the cosmic explosion, a direct glimpse into the first fleeting fraction of a second. The hunt for this signal became one of the most intense pursuits in modern cosmology. The search reached a fever pitch in 2014 with the BICEP 2 collaboration. Using a specialized telescope at the South Pole, the team announced a monumental discovery. They believed they had found the telltale swirl of B-mode polarization in the cosmic microwave background. The scientific world erupted with excitement. Headlines proclaimed that evidence for inflation and gravitational waves had been found, a discovery worthy of a Nobel Prize. It seemed as if we had finally touched the moment of creation, confirming the most radical part of the inflationary story. The signal appeared strong and clear, exactly what theorists had been hoping to see for decades. For a brief, exhilarating moment, it felt like the final piece of the cosmic puzzle had fallen into place. But the universe is a messy place, and groundbreaking discoveries require extraordinary scrutiny. The initial euphoria soon gave way to a more complicated reality. Other scientists quickly pointed out a potential contaminant, one that could perfectly mimic the signal BICEP 2 had detected. Our own Milky Way galaxy is filled with cosmic dust, tiny grains that can also polarize light. This interstellar dust, when magnetically aligned, can create its own B-mode pattern, a foreground fog obscuring the pristine cosmological signal. When the Planck satellite released its own detailed map of this galactic dust, the story changed. The two teams collaborated on a joint analysis, and the conclusion was sobering. A significant portion, if not all, of the BICEP 2 signal could be explained by this local galactic interference. A primordial whisper had been drowned out by the background static of our own cosmic neighborhood. This episode was not a failure, but a masterclass in how science truly works. It highlighted the immense challenge of this ultimate detection, separating the faint echo of the Big Bang from the foreground noise of our galaxy requires instruments of incredible sensitivity and multi-frequency observations to filter out the contaminating effects of dust. The quest for primordial gravitational waves continues with more powerful and sophisticated experiments, each one pushing the technological envelope. The initial disappointment only sharpened the resolve of cosmologists. The fact that the signal is so faint, so perfectly masked by natural phenomena, tells us something profound about the energy scale of inflation itself. The hunt continues, a meticulous search for the faintest of twists in the oldest light, a twist that would finally allow us to hear the echo of spacetime's first shudder. While we were mapping the afterglow of creation, a far more unsettling picture of the present universe was coming into focus. The story of the Big Bang and inflation is not just about how it all began, but what it all is. And the answer is profoundly strange. The atoms that make up everything you can see, from the screen in front of you to the most distant galaxy, account for less than 5% of the cosmos. The rest is a complete mystery, a cosmic embarrassment of invisible ingredients we call dark matter and dark energy. The first clues to this shadow universe emerged not from the ancient light of the Big Bang, but from watching how modern galaxies behave. In the 1930s, astronomer Fritz Zwicky was studying the Coma cluster, a vast collection of galaxies. He noticed that these galaxies were moving so fast that the cluster's gravity should not have been able to hold them together. It was as if the cluster was being held together by the gravitational glue of some unseen, massive substance, which he dubbed dark matter. Decades later, Vera Rubin provided even more compelling evidence by charting the rotation of individual spiral galaxies. Just as planets orbit the Sun faster the closer they are, stars on the outer edges of a galaxy should orbit more slowly than those near the center, but Rubin's observations revealed something astonishing. The stars at the edge of galaxies were whipping around just as fast as those near the core. The only possible explanation was that each galaxy was embedded within a gigantic, invisible halo of matter, a halo that extended far beyond the visible stars, providing the extra gravitational pull to keep the outer stars from flying off into space. This dark matter does not emit, absorb, or reflect any light. It simply clumps together under gravity, acting as the invisible scaffolding upon which the visible universe is built. Without its gravitational influence, galaxies would never have formed from the seeds planted by inflation. Yet, for all its importance, we still have no idea what it is made of. It is a ghost holding the cosmos together, and if that was not strange enough, an even bigger shock was waiting in the depths of space. the hunt for dark matter was only the beginning of the cosmic shock. As astronomers peered deeper into the universe, they expected to find a cosmos slowing down, its expansion gradually braked by the relentless pull of gravity. Instead, they found the opposite. The universe was not just expanding, it was accelerating, flying apart faster and faster as if pushed by some unseen repulsive force. This discovery was so radical it upended our most fundamental assumptions about cosmic destiny. The evidence came from a specific kind of stellar explosion, a Type 1, a supernova. These are thermonuclear blasts of white dwarf stars that always release the same intrinsic amount of light, making them perfect standard candles for measuring vast cosmic distances. Two independent teams, one led by Saul Perlmutter and the other by Brian Schmidt and Adam Rees, were using these supernovae to measure how much the universe's expansion had slowed over time. They pointed their telescopes to the most distant and therefore ancient stellar explosions they could find. By measuring how much the light from these supernovae was stretched or redshifted by the expansion of space, they could calculate how fast the universe was expanding in the past. They then compared this to the expansion rate of closer, more recent supernova. The results were not just surprising, they were staggering. The distant supernova were significantly fainter than they should have been if cosmic expansion was merely coasting or slowing down. The only possible explanation was that the universe was expanding more slowly in the past than it is today. The expansion rate was speeding up. It was as if you threw a ball into the air, and instead of falling back down, it shot away from you faster and faster, defying gravity itself. This discovery earned the teams the Nobel Prize in Physics in 2011, but it left cosmologists with a monumental question. What force could possibly be stronger than the collective gravity of the entire cosmos, pushing galaxies apart? The answer was given a name: dark energy. This is not a substance like dark matter, but rather a property of space itself, a mysterious pressure inherent to the vacuum of empty space. According to Einstein's old equations, such a repulsive force was mathematically possible, though he initially considered it his greatest blunder. Now it appears to be the dominant component of the universe, making up about 68% of everything. Dark energy's existence has profound and chilling implications for the ultimate fate of the cosmos. If this acceleration continues unchecked, the universe will not end in fire or ice, but in a profound and everlasting isolation. Distant galaxies will eventually be pushed away so fast that their light can never reach us. The cosmic horizon will shrink, and far future civilizations will see only their own galaxy in a vast, black, empty void, with no evidence of a Big Bang or any other galaxy, forever lost to the accelerating dark. The universe was a seething nuclear furnace for less than 20 minutes. In that fleeting cosmic moment, the entire periodic table was almost stillborn. As the cosmos expanded and cooled from its initial unimaginable heat, it reached a temperature where protons and neutrons could begin to stick together, forging the first atomic nuclei. This process, known as Big Bang nucleosynthesis, was a frantic race against time. For a brief window, the universe was hot and dense enough for nuclear fusion to occur everywhere at once, but it was expanding so rapidly that this window slammed shut almost immediately. In those first 3 minutes, nearly all the neutrons in the universe were captured to form the cores of the lightest elements. Protons, which are single hydrogen nuclei, remained abundant. Some protons and neutrons fused to form deuterium, the heavy form of hydrogen. Most of this deuterium then quickly fused into helium-4, the most stable light nucleus. Trace amounts of other isotopes were also forged, like helium-3 and a tiny trickle of lithium-7. And then it all stopped. The universe had become too big and too cold for further fusion. The cosmic forge had shut down, leaving behind a primordial soup of about 75% hydrogen and 25% helium by mass, with only minuscule traces of anything else. This prediction is not a rough guess. It is an exquisitely precise calculation based on the known laws of nuclear physics and the conditions of the early universe. The theoretical prediction for the amount of helium-4, for instance, is 24.85%. When astronomers measure the abundance of helium in the oldest, most pristine clouds of gas in the universe, regions untouched by the later element forging of stars, what do they find? They find 24.85%. The agreement is nothing short of spectacular. The same holds true for the other light elements. The predicted tiny amounts of deuterium and lithium align almost perfectly with the observed values from ancient astronomical sources. This concordance of light elements is one of the three great pillars of evidence for the Big Bang, standing alongside the cosmic expansion and the cosmic microwave background. It is a direct quantitative link back to the universe's first 3 minutes. Think of it as the universe's original chemical fingerprint, a fossilized recipe from a time before stars existed, perfectly preserved in the composition of the oldest gas clouds. This incredible match between prediction and observation tells us that we truly understand the physics of the universe back to a time when it was just a few minutes old. It confirms the hot, dense beginning of everything, yet this same success also highlights a profound mystery. The Big Bang only made the three lightest elements. Everything else, every atom of carbon, oxygen, nitrogen, and iron that makes up our bodies and our world, was forged later in the hearts of stars and in the violent explosions of supernova. We are literally made of stardust, but the stage for that stellar drama was set by a perfect 20-minute nuclear fire that blazed across the entire cosmos. But those tiny quantum ripples, magnified by inflation, needed a force to sculpt them into the grand design we see today. That force was gravity. Over billions of years, the slightly denser regions predicted by inflation began to pull in more and more matter, both the visible kind and the mysterious dark matter. These regions acted as cosmic seeds, growing steadily as the universe expanded. The result is not a random scattering of isolated galaxies, but an architecture of breathtaking scale and complexity, a vast cosmic web. This web is made of enormous filaments of dark matter and galaxies, stretching across billions of light years like the strands of a spider's web. These filaments connect at dense nodes where thousands of galaxies swarm together in massive clusters. And between these structures lie the great cosmic voids, immense, nearly empty regions of space that can be hundreds of millions of light years across. This is the large-scale structure of the universe, a foam-like pattern that is the largest known pattern in nature. We can now map this cosmic geography through ambitious sky surveys, which chart the positions of millions of galaxies. When you plot them in 3 dimensions, the pattern emerges clearly, a delicate tracery of light against the darkness, a fossilized imprint of the universe's initial conditions. The most incredible part of this story is the direct line it draws from the quantum to the cosmic. The specific pattern of the web, the statistical distribution of the filaments and voids we measure today, matches the pattern of the tiny temperature fluctuations in the cosmic microwave background with stunning fidelity. The microscopic quantum jitters from the first fraction of a second were the blueprint. Gravity was the contractor that took that blueprint and built the universe we inhabit, a universe of magnificent structure emerging from the faintest of whispers. Edwin Hubble's discovery was a seismic shift in human thought. He found that distant galaxies are not static islands in space, but are all rushing away from us, their light stretched to redder wavelengths as space itself expands. The farther away a galaxy is, the faster it recedes. This relationship, described by the Hubble constant, became the cornerstone of modern cosmology. It is the number that tells us how fast the universe is growing, the very rate of the cosmic expansion itself. For decades, astronomers have worked to pin down this number with ever greater precision, believing it would give us a clear and consistent timeline for the cosmos. Yet this quest for a single, reliable number has instead revealed a troubling rift at the very foundation of our understanding. two of the most trusted methods for measuring the Hubble constant are now in sharp, persistent disagreement. One approach looks into the deep past using the detailed map of the cosmic microwave background from the Planck satellite. By studying the subtle patterns in this ancient light, scientists can calculate the ingredients of the universe and run the cosmic film backward to predict its expansion rate today. This method gives us a value from the universe's infancy. The other approach builds a cosmic ladder step by step into the present. It uses nearby stars and supernova as standard candles, meticulously measuring distances to galaxies to see how fast they are moving away from us right now. This method measures the universe as it is today. Both methods are exquisitely precise and both are performed by world-class teams, but they do not agree. The expansion rate measured directly in the modern universe is significantly faster than the rate predicted from the early universe's afterglow. This is not a small margin of error. It is a glaring tension that has withstood years of re-examination and improved data. It is as if you carefully calculated how fast a tree should be growing based on its seedling stage, only to go out and measure the mature tree and find it is noticeably taller than your calculation predicted. Something does not add up. This Hubble tension suggests one of two things. Either there is a hidden systematic error in one of the measurements, a subtle flaw that the world's best scientists have yet to uncover. Or more thrillingly, this discrepancy is a clue. It could be the first tangible evidence of something missing from our standard model of cosmology, a hint of new physics waiting to be discovered. Perhaps dark energy is not constant but evolving, or maybe a new type of neutrino or a previously unknown interaction was at play in the early cosmos. The tension is not a crisis but a beacon guiding us toward a deeper truth about the strange cosmos we call home. For hundreds of millions of years after the Big Bang, the universe was a featureless, silent sea of darkness. The cosmic fog of neutral hydrogen atoms, which had formed when things first cooled down, hung thick and impenetrable, absorbing any light that tried to travel through it. This was the cosmic dark ages, a time before any stars had switched on. But this profound darkness could not last forever. Out of the subtle density variations sown by inflation, the first structures were slowly coalescing, pulling in vast clouds of gas. When the first star finally ignited, it did not just bring light, it brought a cosmic revolution. These first stars were not like our sun. They were behemoths, hundreds of times more massive, burning ferociously hot and dying young in spectacular supernova explosions. They flooded the cosmos with a torrent of ultraviolet radiation, a brutal, searing light that began to tear apart the surrounding fog of neutral hydrogen. One by one, the electrons were ripped from their protons in a process called reionization. The universe was being transformed from an opaque murk into the crystal-clear, transparent expanse we see between galaxies today. This epoch of reionization was the universe's great unveiling, the moment the cosmic curtains were drawn and light could finally travel freely across the cosmos. But how did this happen? Did a few brilliant early stars do all the work, or was it the collective effort of the first galaxies, their brilliant hearts blazing away? This is not just a question about ancient history. Understanding reionization is the key to knowing how the first stars and galaxies assembled themselves out of the primordial darkness. Our most powerful telescopes are now straining to look back into this twilight era, searching for the faint, redshifted glow of those first stellar nurseries. Every new observation brings us closer to witnessing the cosmic dawn, the moment the lights first came on and the universe as we know it truly began. The quantum realm is a place of wild, unpredictable energy. At the tiniest scales, empty space is never truly empty. It is a seething foam where particles and antiparticles constantly pop into and out of existence, a frantic dance of creation and annihilation governed by chance. This chaotic jitter is known as a quantum fluctuation, a fleeting hiccup in the fabric of reality. In our everyday world, these events are utterly insignificant, far too small and brief to have any noticeable effect. But in the first sliver of a second after the Big Bang, during the inflationary burst, the rules of the game were rewritten. The field responsible for driving inflation, the inflaton field, was itself subject to these unavoidable quantum tremors. Tiny, random variations in its energy density flickered everywhere. Under normal circumstances, they would have vanished as quickly as they appeared. But inflation's hyper-stretching of space acted like a cosmic amplifier, locking these microscopic wrinkles in place and stretching them across the cosmos. A quantum ripple that was once smaller than a subatomic particle was, in an instant, inflated to a size spanning thousands of light-years. What was once a fleeting statistical blip became a permanent macroscopic feature of the universe. These amplified quantum fluctuations translated directly into minuscule differences in density, regions that were ever so slightly more or less dense than their surroundings. They became the cosmic seeds, the fundamental blueprint for all structure. After inflation ended, gravity went to work on this faint imprint. Over hundreds of millions of years, the slightly denser patches began to pull in more and more matter, both dark and visible. They grew steadily, like snowballs rolling down an infinite hill, gathering mass. The densest knots eventually collapsed under their own gravity to form the first stars and the swirling proto-galaxies. The entire cosmic web of clusters, filaments, and vast voids was woven from this underlying quantum tapestry. This is perhaps the most profound connection in all of science. The grandest structures we see in the heavens, the majestic spiral of a galaxy, the brilliant glow of a star, the very planet we stand on, owe their ultimate origin to random, unpredictable jitters in the quantum foam of the primordial universe. Our existence is written in the language of quantum probability, a lottery win on a cosmic scale that was stretched across the sky. This quantum genesis story leads to an even more staggering possibility. If inflation could happen once, stretching a tiny patch of reality into our entire cosmos, what is to stop it from happening again, elsewhere? Some versions of the inflationary theory suggest this process is not a single, one-time event, but an endless, self-replicating chain reaction. This is the concept of eternal inflation, and it gives rise to one of the most mind-bending ideas in all of science, the multiverse. Picture a vast, bubbling cosmic foam forever boiling. In this picture, the overall inflationary energy field never completely turns off. It continues to expand at an unimaginable rate, but within this frenzied background, random quantum fluctuations can cause localized patches to drop out of the hyper-expansion. When a patch drops out, the inflationary energy within it decays, releasing its pent-up potential to create a hot, dense soup of particles and radiation. That patch becomes a universe, a single bubble in the infinite foam. Our entire observable cosmos, with all its hundreds of billions of galaxies, is just one such bubble, one pocket universe that formed when our local region of inflation ended. But the greater background continues to inflate eternally, and new bubbles are constantly popping into existence, each one disconnected from the others, each one a separate universe with its own unique history. The truly profound implication is that the random quantum jitter that ended inflation in our patch would have been different in other patches. This means the fundamental constants of nature, the very laws of physics themselves, could be set to different values in each of these bubble universes. In one bubble, the force of gravity might be 10 times stronger, causing stars to burn out in a flash. In another, the nuclear forces might be too weak to allow atoms to ever form. We happen to live in a bubble where the constants are just right for atoms, planets, and life to emerge, a concept often called the anthropic principle. The multiverse idea transforms our perspective entirely. The deep mysteries of our universe, like why the laws of physics seem so finely tuned for our existence, may have a simple, if humbling, answer. There is no fine tuning. We simply reside in one of the rare bubbles where the random dice roll produced a habitable cosmos, and we are here to observe it. This is not a testable scientific hypothesis in the traditional sense, as these other universes are forever beyond our observational reach. It is instead a dramatic philosophical consequence of our most successful theories of the very beginning. It suggests that our Big Bang was not the beginning of everything, but merely our local beginning, one note in an infinite, eternal cosmic symphony. This fine-tuning of our universe for life points toward a problem so profound it is often called the worst theoretical prediction in the history of physics. We have measured the strength of dark energy, the force accelerating cosmic expansion. It is incredibly small, a faint, persistent push across the vast emptiness of space. But when we try to calculate the energy of that emptiness using our well-tested laws of quantum mechanics, we get a number that is not just a little bit off. It is wrong by a factor of 1 followed by 120 zeros. This is the cosmological constant problem, and it represents a staggering disconnect between our two most successful theories, quantum mechanics and general relativity. Think of it this way: the vacuum of space is not truly empty. According to quantum field theory, it is a turbulent sea of virtual particles flickering in and out of existence. Every cubic centimeter of this quantum foam should be bursting with an enormous intrinsic energy, exerting a powerful gravitational repulsion. This theoretical vacuum energy is the natural candidate for the cosmological constant, the source of dark energy. But the observed dark energy is unimaginably weaker. It is like calculating that the air pressure in a balloon should be enough to crush a battleship, only to measure it and find it has the gentle push of a single breath. How can the energy of the vacuum be so close to zero, yet not perfectly zero? This unnaturally small value is what allows galaxies to form and life to exist. If it were anywhere near its predicted quantum value, the universe would have been ripped apart in a violent explosion before the first atoms could even form. The fact that it is so finely set to a value that permits our existence is a mystery that keeps physicists awake at night. Some believe a new symmetry of nature must exist, one that perfectly cancels out the vacuum energy to nearly nothing. Others suggest that the dark energy we see is not a fundamental constant at all, but a dynamic field that has slowly decayed over cosmic time. A more radical proposal is that our understanding of gravity is incomplete, and that Einstein's theory of general relativity needs modification on the largest scales. This embarrassing discrepancy is not just a small detail. It is a glaring signpost pointing toward a deeper layer of reality, a fundamental theory that will one day unite the quantum world with the cosmic realm. Frozen into the very architecture of the cosmos is a ghostly echo of its earliest sound. This discovery, known as baryon acoustic oscillations, gives us a cosmic ruler of incredible precision. To understand it, we must go back to the universe's first few 100,000 years, when it was a hot, dense plasma of light and matter. In this primordial soup, photons and particles of ordinary matter, called baryons, were locked in a violent tug of war. Gravity would try to pull the baryons into the denser regions seeded by inflation, but the intense pressure from the trapped photons would push them back out. This created a series of pressure waves or sound waves that rippled through the young cosmos. These waves traveled outward at over half the speed of light until a critical moment when the universe cooled enough for atoms to form, and the photons streamed away as the cosmic microwave background. At that instant, the waves froze in place, leaving a permanent, spherical imprint in the distribution of matter. Each wave left a shell of matter, a faint overdensity, at a very specific distance from its center. That distance, the sound horizon, became a standard ruler etched across the sky. Today, we can see this fossil pattern by mapping the positions of millions of galaxies. When we analyze their distribution, we do not see a random scatter. Instead, we find that galaxies are slightly more likely to be found separated by that specific distance, the radius of those ancient sound waves. It is as if the universe is stamped with a uniform pattern, like the regular spacing of ripples from a raindrop in a pond, but on a scale of nearly 500 million light-years. By measuring the apparent size of this standard ruler at different cosmic epochs, we can chart the expansion history of the universe with phenomenal accuracy. It provides an independent and powerful confirmation of dark energy, showing us how the stretching of space has changed over billions of years. This cosmic echo, a fossilized sound wave from the dawn of time, continues to guide us, whispering the secrets of the universe's geometry and its accelerating fate. Yet this pristine fossil record of the Big Bang holds one small, stubborn flaw. The universe's first nuclear forge seems to have produced too much of one particular element, or perhaps our telescopes are not seeing all that remain. This is the lithium problem. According to our most precise calculations of Big Bang nucleosynthesis, the frantic fusion in those first few minutes should have created a specific trace amount of a light isotope called lithium-7. When we look at the oldest stars in our galaxy, stars that formed from the primordial, uncontaminated hydrogen and helium, we should see this predicted lithium abundance preserved in their atmospheres like a time capsule. But we do not. The amount of lithium-7 we actually observe is only about 1/3 of what the theory says it should be. A large chunk of the universe's original lithium is simply missing. This is not a catastrophic failure of the Big Bang theory. The predictions for hydrogen, helium, and deuterium are spectacularly accurate. It is more like finding a single, frustrating typo in an otherwise perfectly translated ancient manuscript. So where did the lithium go? Cosmologists and astrophysicists have proposed several intriguing solutions. One possibility is that our understanding of nuclear physics is incomplete, and some unknown particle, like a certain type of neutron-less neutrino, interacted with the primordial soup and altered the nuclear reaction rates. Another, more stellar explanation is that these ancient stars are not the perfect time capsules we thought they were. Over their billions of years of life, their internal processes may have slowly dragged surface lithium down into their hotter interiors where it was destroyed. Or perhaps these stars have churning outer layers that mix and dilute the lithium, hiding it from our view. This small discrepancy serves as a vital reminder. Even our most successful cosmic theories can contain hidden wrinkles, tiny anomalies that whisper of deeper, undiscovered physics. The lithium problem is a ghost in the machine of the Big Bang, a faint but persistent signal that our picture of the cosmic dawn, for all its brilliance, may still be missing a crucial piece. Even our most perfect cosmic map is not without its strange and unsettling features. Tucked within the exquisite data of the cosmic microwave background, there exists a peculiar set of alignments so provocative that scientists gave it a dramatic name, the axis of evil. This is not a literal axis of darkness, but a curious statistical oddity. The temperature fluctuations in the ancient light appear to align across the sky in a way that seems to pick out a preferred direction, a kind of cosmic tilt that should not exist. According to our most fundamental assumption, the cosmological principle, the universe should be isotropic. This means it should look the same in every direction, with no special place or orientation. The axis of evil, if it is real and not a statistical fluke, gently tugs at that foundational pillar. How could the entire universe have a preferred alignment? One speculative idea is that this alignment is a cosmic fossil, a scar from a time before inflation began. Perhaps the tiny patch that inflated into our universe was not perfectly symmetrical, but had a slight preferred direction imprinted upon it from some earlier, more chaotic state of reality. When inflation stretched that patch to cosmic proportions, it stretched that directional preference along with it, leaving a faint, ghostly orientation painted across the entire sky. Another possibility is that these alignments are a window into something even more exotic, like the very topology of space itself. Could the universe be finite and have a complex shape like a hall of mirrors, causing patterns to repeat and align in strange ways? While most cosmologists believe the axis of evil will likely fade with more precise data, a simple artifact of how we analyze the map, its persistent whisper reminds us that our core assumptions must always be tested. It stands as a challenge, a hint that the first moment of creation might hold complexities we have only begun to dream of. This incredible period of hyper-expansion could not last forever. The very mechanism that drove inflation also contained the seeds of its own destruction. The inflatoned field, the strange energy that caused space to stretch so violently, was inherently unstable. Picture a marble resting precariously at the very peak of a steep, smooth hill. This represents the high energy state that powered inflation. It was a false vacuum, a temporary and unnatural condition. All it took was one tiny quantum nudge and the marble began to roll. As the inflatoned field decayed, tumbling down its energy hill, it began to oscillate wildly. Every point in space became a frenzied oscillator, and with this frantic wobbling, the immense energy that had been locked in the field was released in a catastrophic burst. This is the moment of reheating, the violent end of inflation that gave birth to the traditional hot Big Bang. All that potential energy which had been stretching the fabric of space was now violently transferred, flooding the universe with a searing, dense soup of fundamental particles and radiation. In an instant, the cold, empty expanse of the inflating universe was transformed into a blistering hot plasma, a primordial fireball. The temperature skyrocketed, reigniting the cosmos and setting the stage for everything that would follow. How exactly did this happen? Theorists propose different models for this violent transition. In some scenarios, the decay was instantaneous and explosive, a single, universe-wide shudder that filled space with matter. In others, it was a more gradual process, like a series of rolling waves of energy release. This reheating phase was the true beginning of the cosmos as we conceptualize it, the moment the clock of the hot Big Bang truly started ticking. It was the ultimate cosmic reset, transforming the weird, stretched geometry of inflation into the familiar, particle-filled universe whose story we can trace through nucleosynthesis and the cosmic microwave background. Without this dramatic end to inflation, our universe would have remained a cold, empty, and ever-stretching void, forever devoid of the heat and structure needed for stars, planets, or life itself. This hypothetical agent of cosmic expansion is known as the inflatoned field. It is not a substance you could touch or see, but rather a kind of energy field that is thought to have permeated all of space in the first instant. Think of it as a kind of cosmic fuel, an engine whose immense potential energy had a bizarre gravitational effect, causing space to stretch at an ever-accelerating rate. The shape of this field's energy landscape is the key to everything. Picture a gentle, sloping hill. At the very top of this hill, the inflatoned field was trapped in a high-energy state, a condition known as a false vacuum. This state possessed a peculiar property, a negative pressure so powerful that it generated a repulsive gravity, forcing space to expand exponentially. As long as the field remained perched on that high plateau, inflation continued, doubling the size of the universe again and again in a fraction of a microsecond. But this state was inherently unstable, like a marble balanced perfectly on the crest of a dome. A random quantum fluctuation finally gave it the nudge it needed to start rolling. The field began to slowly tumble down its energy hill. As it rolled, the energy stored in the field was converted into a frenzy of motion. And when it finally reached the bottom, that colossal potential energy was released in a cataclysmic burst. This moment, known as reheating, was the true beginning of the hot Big Bang. The inflatoned field's wild oscillations at the bottom of the hill acted like a billion cosmic bell ringers. their energy shaking the fabric of reality and flooding the universe with the primordial particles and radiation that would eventually coalesce into everything we see. The entire visible cosmos, every atom and photon, is the decay product of this single, all-powerful field. Yet for all its importance, the inflaton remains entirely hypothetical. Its true identity is the holy grail of modern cosmology. Is it a fundamental force we have not yet discovered, or perhaps a combination of known fields acting in concert? Unlocking the nature of the inflaton would mean finally understanding what set our entire reality into motion. Yet for all its explanatory power, inflation is not the final word. Every great scientific theory must withstand challenges, and this one is no exception. While it remains the leading framework for understanding the universe's first moments, a growing number of physicists point to its unresolved puzzles and propose radically different origins for our cosmos. The primary challenge is that inflation is almost too successful. It can explain a wide range of outcomes, but its flexibility makes it difficult to pin down with a single, definitive test that would rule out all other possibilities. How did inflation even begin? The theory requires the universe to start in a very specific, highly ordered state, a problem of initial conditions that some argue simply pushes the mystery of the beginning one step further back. This has opened the door for compelling alternatives. One fascinating idea is the bouncing universe model. Instead of a singular beginning from nothing, this theory suggests our universe is cyclical. It posits that a previous cosmos contracted in a big crunch, but instead of collapsing to a point of infinite density, quantum gravity effects caused it to bounce, rebounding into the expansion we see today. In this view, the Big Bang was not a birth but a rebirth, and the smooth, flat geometry we observe is a relic from the immense compression of the previous cycle. Another, even more radical class of theories suggests that spacetime itself is not fundamental. In these emergent gravity scenarios, space and time are collective phenomena that arise from the entangled interactions of countless microscopic components, much like the temperature of a gas emerges from the jostling of its molecules. In such a world, the Big Bang marks the moment when this cosmic tapestry wove itself into existence, and inflation, if it happened at all, was a consequence of this deeper underlying process. These alternatives are not yet as developed as inflation, but they represent vital and creative efforts to grapple with the ultimate question. The true strength of science lies in this vibrant debate, this relentless questioning of even our most cherished ideas. The story of our cosmic dawn is still being written, and the next chapter may well come from a direction we have not yet even considered. The next generation of cosmic detectives is already preparing for the ultimate hunt. Across the high deserts of Chile and atop the frigid Antarctic plateau, a new ground-based observatory known as CMB-S4 is under development. It is not a single telescope, but a coordinated army of them, designed to scan the sky with an unprecedented 500,000 detectors. Its mission is to scour the cosmic microwave background with a sensitivity that dwarfs all previous efforts, searching for the faint, twisting signature of primordial gravitational waves. Simultaneously, high above the distorting effects of our atmosphere, the Japanese-led Light BIRD satellite is being readied for launch. This space-based observatory will map the entire sky in exquisite detail, free from the interference of earthly weather and atmospheric noise. Together, these projects represent a colossal leap in our technological reach. Their goal is to filter out the confounding signals from galactic dust with such precision that any remaining B-mode polarization must be the real thing, the long-sought echo from inflation itself. They are listening for a whisper so faint that it has eluded us for decades, a signal buried under layers of cosmic static. A definitive detection would be one of the most profound discoveries in the history of science, allowing us to peer directly back to that first sliver of a second and confirm the violent stretching of space-time. It would tell us not just that inflation happened, but at what energy scale it occurred, revealing the specific physics that powered the birth of our universe. This is the cutting edge where the grandest questions of our cosmic origin meet the most meticulous engineering on Earth, a final, determined push to hear the universe's first cry. The faint echoes of cosmic inflation are not the only whispers in the fabric of space-time. In 2015, a new era of astronomy was born when the LIGO Observatory directly detected gravitational waves for the very first time. These were not the primordial ripples from the Big Bang, but colossal waves generated over 1 billion years ago by the violent merger of two black holes. The detection was a monumental triumph, confirming a key prediction of Einstein's general relativity and opening an entirely new sense with which to perceive the universe. Unlike light, which can be absorbed or blocked, gravitational waves travel virtually unimpeded across the cosmos, carrying with them a pure, undistorted story of the most cataclysmic events. LIGO and its counterparts have since listened to the chirps and rumbles of dozens of merging black holes and neutron stars, each event sending a shiver through the detectors that tells us about the masses and spins of these mysterious objects. But this is just the beginning. While LIGO listens to the high-frequency crashes of individual cosmic disasters, a future mission is being designed to hear a far deeper, more ancient hum. The Laser Interferometer Space Antenna, or LISA, will consist of 3 spacecraft flying in a perfect triangle millions of kilometers apart, connected by lasers. This gigantic observatory, floating in the quiet of space, will be tuned to the low-frequency gravitational wave spectrum. Here, in this quiet register, scientists hope to find something truly revolutionary, a stochastic background. This is not the chirp of a single merger, but a cacophony of countless tiny waves overlapping into a steady hiss, like the collective sound of a vast ocean. This background hum could be the combined signal from every binary white dwarf star in our galaxy, but it might also contain something far more precious, the faint, red-shifted rumble from the universe's very first second. If the violent end of inflation shook space-time like a thunderclap, that signal would have been stretched and diluted over billions of years into this pervasive, low-frequency whisper. Detecting this primordial background would be the ultimate confirmation of cosmic inflation, a direct recording of the Big Bang itself. It would open a window onto energies and timescales that are forever hidden from traditional telescopes, allowing us to listen for the first time to the very birth cries of our reality. From a single point smaller than an atom, our universe has unfolded into a cosmic tapestry of billions of galaxies, each one a testament to a violent and beautiful genesis. This journey through 25 incredible discoveries reveals a story more fantastic than any myth, a narrative written in the oldest light and woven into the fabric of space itself. We have traced the path from a hot, dense fireball to the vast, structured cosmos we observe today. The cosmic microwave background gave us a baby picture of the universe. Inflation explained its impossible uniformity and perfect flatness. Quantum fluctuations stretched to cosmic proportions provided the seeds for every star and galaxy. We have confronted the shadowy realms of dark matter and dark energy and felt the tension in the Hubble constant that hints at physics beyond our current grasp. Each discovery is a thread, and together they weave a coherent and breathtaking picture of our origins. The human drive to understand, to look up at the night sky and ask where it all came from, has brought us to the brink of comprehending the very first moments of everything. It is a quest that connects us to the cosmos in the most profound way, for we are not just living in the universe, we are the universe awakening to itself. So we turn this final reflection over to you. Of all these cosmic revelations, which one reshaped your understanding of reality the most? Was it the sheer improbability of our fine-tuned existence, or the echo of quantum jitters that grew into galaxies? Share the discovery that amazes you in the comments below, and if you are hungry for more journeys to the edge of understanding, Be sure to subscribe for our next deep dive into the universe's greatest mysteries.